Okay, now that we know that the simplex method works, I guess we should begin talking about how well it works. We should begin sort of easing our way into a discussion of actually implementing the simplex method. I think I originally called the lecture performance. I guess I didn't mean that. Really what I want to talk about in this lecture is the computational complexity of the simplex method. So performance could be interpreted to mean, if I have a solver that I've written and I want to run it on some input, how long does it take? And that's a function of a lot of different factors. Namely, as you know from previous courses, if we begin analyzing the complexity of something in terms of its worst case running time, that doesn't necessarily tell us how it's going to perform in practice, because and it turns out this is the case with the simplex method. There are many algorithms whose worst case running time is much worse than their expected case running time, because the worst case inputs are relatively few and far between. So what I want to talk about, before we can talk about implementation specifics, so how to make a specific implementation of the simplex method run fast, we should talk about things like the worst case inputs, or we should at least try and put some bounds on how slow the simplex method is going to be in the worst case. We now know that at least it's not going to run forever. At least it's going to terminate after a finite number of steps, as long as we use a pivot rule or some other adjustment to the algorithm that prevents cycling. So as this slide is pointing out, we've now proven that the simplex method is a general purpose LP solver. And so we want to talk now about, okay, so suppose we're going to write an implementation of the simplex method. How long do we expect it to take? In the worst case and in practice, so on the type of LP you would tend to see in a practical setting. So in order to analyze an algorithm, I have to be very careful to define the problem very specifically and thoroughly, because otherwise I'm making claims that I can't necessarily back up. So I not only have to do that, but in a minute I'm also going to have to define what it means to analyze something, because there are lots of different ways of analyzing algorithms. So we are going to talk about, given an LP in standard form, which has n optimization variables and m constraints. I'm writing this in matrix notation, both because it's more compact and because I think after the last lecture we're all a little bit fed up with looking at the LP in terms of a dictionary or a huge number of variables with different names. So maybe it's nice to use a more compact notation. What I want to do is I want to analyze the running time of the simplex algorithm in terms of just n and m, in terms of the number of variables and the number of constraints, and that's it. As you know from analyzing algorithms in the past, and from what we've seen about the simplex algorithm so far, certainly there are other factors that could contribute to the linear program besides simply its size that could affect the running time. And we'll come back to this a little bit later, and it'll factor into your programming project. It turns out that in practice, it's very common to use an LP solver to solve an LP that has 1,000 variables and 1,000 constraints, but where the constraint system is extremely sparse, where the matrix A is full of zeros, so that there are relatively few non-zero entries. It turns out that if we know that in advance, we can plan ahead. We can design algorithms that are faster on sparse systems of constraints. So of course that impacts the running time in a more specific case, but all I care about is the general analysis. If all you tell me is the number of variables and number of constraints, how fast or slow can I expect the simplex algorithm to be? The other side of the coin is, what does it mean to analyze an algorithm? And what this slide is actually saying is we're going to do the same level of analysis that you would do in CSC 225. And if you've taken algorithms courses since then, so if you've taken the various fourth year algorithms courses like 425, or maybe randomized algorithms 423, or some of these exotic flavors of algorithms courses that haven't been offered in a few years, if you've taken courses like this, you know that there are lots of occasions where you might analyze an algorithm and you'd be analyzing it in a different model of computation than we use in CSC 225. So the model that we tend to use in CSC 225 is what's called the random access model, and it basically amounts to, let's analyze an algorithm for the purposes of implementing it on a computer like the computer you're using right now to watch this video. So common assumptions would be, if I store something in memory, then I can retrieve that item in constant time. So again, the memory is random access. Doesn't matter where it is in memory, and obviously in algorithm analysis, we often don't care that much. If it's in memory, retrieving it from memory or putting it in memory is constant. Now, just for the sake of having perspective, the alternative might be something like if we're working with a Turing machine, where our memory is a paper tape, it might take longer to go get something if it's further away. We don't worry about that. We didn't worry about that in CSC 225 either. Similarly, there's this issue, if I'm analyzing an algorithm in terms of some operation, then, like, is it in terms of clock cycles of the CPU? Is it in terms of some other fundamental thing? So what we do in 225 is typically analyze it in terms of some set of common operations that are considered to each individually be constant. The analysis I'm going to do here is just going to be based on the number of basic arithmetic operations, plus, minus, division, and multiplication. This means we will assume, essentially, that those operations are constant time. So we'll just count the number of arithmetic operations and then leave it to somebody else later to decide if it's unrealistic that those be constant time, to adjust the analysis to account for how long those things take. Normally, if we're analyzing algorithms to implement them on this type of computer, the type you're using to watch this video, it is reasonable to assume that arithmetic is constant time because there is some upper bound on the number of clock cycles used to perform arithmetic on whatever primitive type you might use, so int or float or whatever. However, of course it's true that that requires making a bunch of assumptions about the computational model. For example, if I'm using 64-bit ints to represent everything, I suppose it's reasonable that I can't expect my numbers to require more than 64 bits. And if you've taken those higher level algorithms courses, you might know that occasionally we have to analyze algorithms in terms of representing numbers where the number of bits I use in the number has to factor into the analysis of the algorithm because I don't know how big the number is going to be. We're not going to do that here. We're just going to assume, similarly to the model we would use on typical programming applications, we're going to assume that arithmetic is constant. Now, one wrinkle to that, one aspect I should point out, is that assumption does make a great deal of sense when we're talking about using floating point computations, because we know that if we declare a variable of type float or a variable of type double, its size and the length of time required for an operation is bounded, so we can treat it as if it's constant. If we want to use exact rational arithmetic, as I have been doing recently, as I have been insisting that you do recently, then that could complicate things. Because, for example, I could have some value that an x value could be between 0 and 1, and yet x could be some incredibly hideous-looking fraction, 99999 divided by, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 0. Something like this, where the magnitude of x, in terms of, the number x, is between 0 and 1. It's a small magnitude. But if I'm representing it with exact rational arithmetic, I might need a huge number of bits to represent the numerator and denominator, even if I do that in lowest terms. That does complicate things a bit. My claim, first, is that analyzing it with that in mind would complicate things a lot. Like, it would really make the analysis, it would muddy the waters. But also that if we analyze it assuming arithmetic is constant time, then we can always, if you cared, we could always go back later and factor this in. So we're just going to assume, essentially, that all arithmetic is constant time, that we're using some fixed primitive type to represent all of our numerical values, and I want to analyze the simplex method in those terms. So I guess the question then is, what is the simplex method? Like, let's break the simplex algorithm down into pieces and try and figure out the running time of each piece. Fundamentally, I think that the simplex algorithm can be interpreted as a sequence of this iterative sequence of pivoting operations, or individual steps. Each step, though, consists of a few parts. I guess maybe 4 parts. The first 2 parts are sort of, part 1a and 1b. So at each step, actually maybe step 0 would be check status. We could do this at the beginning or the end. At each step of the algorithm, we inspect the dictionary that we're currently looking at, and we decide if we're done. So if, for example, if the dictionary were optimal, then we would be done. So that takes some time to check that. Then I choose my entering variable. And then based on the choice of entering variable, I have to choose my leaving variable. And as I said, this is sort of, really steps 1 and 2 are the same step. I would argue that they're both the same phase of the algorithm. And then finally, we actually perform the pivot. We produce we modify the dictionary based on putting the entering variable in the basis and taking the leaving variable out. So 4 pieces. Basically, what I'm going to conclude here is that this, actually performing the pivot, eats up more time than all the other ones, and therefore that the running time of the pivots, of the actual pivoting, dominates that of everything else. We should still talk about that. So first, if once I've chosen my entering and leaving variables, the actual pivoting step of adjusting my dictionary requires this big theta of this number of operations. So I'm using big theta here. If depending on your background, you might only use big O. If you took 225 here, I think you would have been given, the difference would have been explained to you. If you're used to using big O, then for the purposes of this lecture, whenever you see a big theta, think of it as being very similar, although it's considered to be a more precise notation than big O. So the dictionary itself is what? Let's see, n plus 1 columns by, I guess it's m plus 1 rows. And if I perform an operation that could modify every single element of that dictionary, then clearly the number of things I'm modifying, and therefore the minimum number of operations I have to perform, is n plus 1 times n plus 1, which is big theta of n times m, because the lower order terms in that expansion disappear asymptotically. They're not relevant to us. And so that's where I get the big theta of m times n, because I can easily produce examples of dictionaries and pivots where performing the pivot does indeed modify every single value in the table. And I have one here. So if I do a pivot with, let's see, x1 is my entering variable, and W1 is my leaving variable, I get this new dictionary where every single value is different. So clearly I could actually, it's easy to show I can attain this number asymptotically of operations by performing a single pivot step. It's true that maybe I don't necessarily modify each value only once. I mean, while I'm performing the pivot, I could modify each individual element of the table several times for whatever reason as I perform these row operations. On the other hand, I don't think that would occur n times. I think that would occur some constant number of times. So I think it's reasonable to claim that each pivoting step requires n times m operations. So that is just, once I've chosen my entering and leaving variables, I take the basis row that corresponds to my leaving variables, solve that for the entering variable. That would take big O of n operations. And then I perform the substitution of the solved row into all the other rows, which is, depending on how we view it, we could also view that as an elementary row operation. I would argue that is also big O of n. And then essentially, because I could modify every row of the table, it's reasonable to assume that I could get to big O of n times m time. Okay, so that's how long it takes once I've chosen my entering and leaving variables. Then there's the question of, what about these other steps? Checking the status, deciding if I'm optimal, choosing an entering variable, choosing a leaving variable, and I suppose at step 2, that's also where we would decide to stop if the dictionary turns out to be unbounded, because normally that's where we discover an unbounded variable. My claim is going to be that steps 0, 1, and 2 take so little time compared to this that it just sort of comes out in the wash, that ultimately the time of the entire iteration is dominated by the time of the pivot itself. So to choose the entering variable, well, I mean, I guess that depends on what pivot selection rule we're using. So if we're using a relatively simple rule, Bland's rule or the largest coefficient rule, all we have to do is look at every element of this one row, which of course is, there's n plus 1 things there. Okay, so that's linear. Once I've chosen the entering variable, again, thinking about the largest coefficient rule, then I find the leaving variable by examining everything in the same column as the entering variable, and I guess also this constant column. But doing that would be big O of m. So we'd just be looking at everything, running down one column or two columns, a constant number of columns of the table. And you can see if I've chosen a pivot selection rule that's relatively simple, that means that the running time of choosing both the entering and leaving variables is big theta of n plus m, which asymptotically, as both of those increase, is definitely less than this. I should add, though, we should be careful about a couple of things. So first, we've discussed a bunch of different possible pivot rules. By no means an exhaustive set. There are lots of other options for how to choose pivots. All of the ones we discussed in the previous lecture, besides these two, we could easily show that they can be evaluated in fewer than this number of operations. And so again, as long as we're not using these two, we can definitely, I think, demonstrate that the running time of each individual iteration is dominated by the pivot itself. That said, I've got a bunch of disclaimers. So one, One of the pivot rules we saw last time was this random pivot selection rule. And although, assuming you have a source of randomness, because I have to always say this disclaimer because otherwise people that know about randomness will complain, as long as you have a convenient source of randomness that gives you random numbers quickly, once I can get random numbers, choosing a random entering variable is very easy. I just enumerate the possibilities and choose at random from them, which is big O n, assuming the source of randomness can be evaluated in constant time. On the other hand, that said, although this claim is true even if I consider the random pivot rule, for the rest of this lecture, let's ignore the random pivot selection rule. Because maybe you can appreciate we can't easily do a worst case analysis if randomness is factoring into our algorithm. And we know already that there are all sorts of things that don't really apply if the selection of pivot could be random. Because if I'm using a pivot selection rule like largest coefficient, then cycling could occur. And if cycling occurs, we get an infinite loop. But if cycling doesn't occur, then, if we don't infinitely cycle with a deterministic pivot rule, then we never cycled at all. So if a cycle ever occurs with the largest coefficient rule, it'll go around for infinity. A cycle could occur with random pivot selection and then resolve because randomness allows us to escape from the cycle. That is, if I run the simplex method with the random pivot selection rule and it finishes, if it terminates, that doesn't necessarily mean that it didn't cycle at some point. That's one more reason that it's good to just not think about the random case in this lecture. We won't have time to do the more detailed analysis of the random case anyway, both time-wise and because some people are missing the background. However, one of our books actually talks about it in more detail. It is actually a very interesting thing to think about. And if a grad student wants to talk about that as their presentation topic, that would be great too. When this slide says that all of the rules except for steepest edge and magic can be easily shown to require fewer than m times n operations, I want to clarify I'm not actually saying that steepest edge requires more than that number of operations. Instead, I'm saying that it can't be easily shown to require more. That's all. What I'm really saying here is I don't want to talk about this. I don't want to analyze this rule any further. We know it's complicated, but we haven't seen it in much detail, so we'd rather not. We'd rather leave it out of our analysis. Also, we've seen that if it's used in practice, it's often approximated, and we don't know much about how the approximation is computed, and so instead I'm just going to ignore it. And then finally, there's this. The magic pivot rule isn't designed to be practical. We don't even know of any implementations of it. It's a hypothetical, notional pivot rule that exists for the purpose of drawing some theoretical conclusions. Because we don't know how to evaluate it, we obviously can't easily show that it requires fewer than m times n operations. So I'm going to leave this out of our analysis as well until the end. I'm going to come back and talk about the magic pivot rule again at the end of this lecture. So if we know that performing a single iteration of the algorithm takes big theta of m times n time, then I guess all we have to figure out is how many iterations are necessary in the worst case, assuming the algorithm doesn't cycle, which we now know is a reasonable assumption. There is a way of preventing that. And that really is the biggest unknown that remains. We also know from our own experience that there are plenty of if I start the algorithm on an arbitrary LP, I don't really know how many pivots it's going to take. So we know that the number of pivots required really depends on the LP. So what I want to know is if I look at the LP that creates the worst, that requires the largest number of pivots, how many is that? Can I draw some kind of a bound? We have this theorem, which actually was stated in an earlier lecture, and I only realized when I was preparing to make this video that in fact the real proof of this theorem is in this set of slides. So sorry about that. I've actually sketched this proof out several times by now. I'm therefore not going to go through it in that much detail here, other than just restating it so we remember what it means. So this theorem says and I should of course qualify this, if the deterministic, because we're again ignoring the case where we're choosing random pivots, if the deterministic simplex method with whatever pivot rule you chose does not cycle, then there are at most this number of pivot operations performed. And the reason is basically this. If it does not cycle and the pivot rule is deterministic, then it's impossible that it could visit the same dictionary twice. Because if it starts at some dictionary D1, and here's this diagram again, if it starts some dictionary D1 and ends up back at D1 at any point in the future, it's going to go around in a circle forever. So if it doesn't cycle, then it can never visit the same dictionary twice. And if we can show that the number of possible dictionaries is finite, then we know that that's the maximum number of steps that could be taken. Otherwise, it would repeat itself by the pigeonhole principle. And we saw in a previous lecture, the number of possible dictionaries is equal to n plus m choose n, or alternatively, m plus m choose m. And the reason is because once I've decided what my basic variables are, so if I've decided x1, w1, and w2 are the basic variables, and x2 and x3 are the non-basic variables, the rest of the dictionary is determined completely by that choice. And the way you can verify this is if you start from whatever, come up with some initial dictionary for a problem, and suppose that it doesn't have the same basis and or non-basic variables that this one does, you can always take the initial dictionary and pivot it until you get whatever variables you want into the basis. And the pivot step is deterministic. The pivot step is just solving a set of equations. And as a result, the coefficients in the dictionary are uniquely determined, essentially, by the choice of basic variables and non-basic variables, up to, of course, reordering of rows and reordering of columns, which in my mind doesn't change anything about the character of the dictionary. So really, the number of possible dictionaries, at most, is the number of ways I could choose my basic and non-basic variables. So I've got n plus m variables, n optimization variables, and m slack variables, and I'll choose n of them to be non-basic. Or alternatively, I'll choose m of them to be basic. I just have to make that distinction, and that determines the dictionary. So the number of ways of doing that is the number of possible dictionaries. And it's this number, which is looking pretty nasty. I mean, obviously, if we're going to perform this number of pivoting steps, that is still a big number. So the proof, what I just laid out verbally, is written here. I'm going to skip over it because we've talked about this repeatedly in recent lectures. It turns out, you might have noticed that a minute ago when I was sketching out this idea that if you give me any particular basis, I can get the dictionary for that basis by starting at some other dictionary and just doing a bunch of pivots. And the pivots are reversible solutions. I think I said something like, I'm solving a system of equations. You might have caught on there that I was using language that sounds a lot like linear algebra in disguise. And really, that is what I was saying. It turns out that what I was really saying is that the constraint system is an invertible matrix. And that's why I was so sure of myself when I said that if I give you a basis, that uniquely defines the rest of the dictionary. We're almost at the point in the course where we can come back and actually see this formally. I know that I keep alluding to this idea that linear algebra is going to be a big deal in a little while. We are getting there. So we have this quantity. This is the number of possible dictionaries. So in the absolute worst case, which we will see, we don't realize that, but in the absolute worst case, this is the maximum number of pivot steps that the simplex algorithm can take with a deterministic pivot selection rule, and such that it does not cycle. So what can we do with this quantity to try and make it more tangible? So offline, so just for the sake of having a point of reference here, if m and n are both equal, then it turns out that that's when this quantity gets maximized. And that makes it a lot easier to sort of see what's really going on. So if n equals m, then this just ends up equaling 2n choose n. Or 2m choose m, frankly, but we'll work with n in this case. Because we're now down to only one variable, it's much easier to bound it. A bound that we can put on it, this can be proven via some logic along the lines of a 225 asymptotic proof, which I don't think anybody has too much patience for in this setting. But we can prove this, that 2n choose n is stuck between this number and this one. And in my mind, given how big this is, 2 to the 2n, given how big that is, this dividing it by 2n doesn't really bring it down too much. So in my mind, that really says this quantity is very close to 2 to the 2n. It's certainly exponential, because we can probably, I think you'd agree with me that certainly this is a reasonable conclusion to draw. Certainly, the number of dictionaries is greater than is exponential in n, which is bad news. We obviously would rather our algorithms were not exponential, that their running time were not exponential. And frankly, if they're going to be, I'd much rather have 2 to the n than 2 to the 2n, certainly. So that means, I guess, based on the number of dictionaries that could exist, the number of pivot steps may be exponential in the worst case. But maybe we're catastrophizing here a bit, because we've decided that the simplex algorithm can't hit every dictionary twice, or any dictionary twice. Therefore, this is a strict upper bound on the number of steps it can take deterministically. but maybe we're being, I don't know, we're being a little bit pessimistic there. Because it's true, yes, if it doesn't cycle, the algorithm can't hit the same dictionary twice. But if it doesn't cycle, is it really realistic that it's going to hit every dictionary once? I don't think so. So let's think of the reasons why I think it's acceptable to rule out that the simplex method really could go to every possible dictionary for a particular LP. So one of them is we've seen that the algorithm steps through lots of dictionaries, but there are also lots of dictionaries for an LP that correspond, for example, to infeasible points. There are infeasible dictionaries, and we know that if we start the simplex method, it's never going to go from a feasible dictionary to an infeasible one. So that's one reason that the simplex method would not visit every possible dictionary. But there's another reason. So suppose I've got two vertices of my polytope, and my objective function, the gradient, points straight up. And I start down here, and for whatever reason, I pivot. So I'm going to write, this is saying f of x equals, we'll call it z. And over here, the objective value is exactly the same. In other words, suppose our polytope, maybe it was this diamond shape here. And I start down at my initial vertex, and my optimal solution is this one. And both of these two vertices have the same objective value. And we know, because we've talked about pivot rules, that because the way these things work, maybe, I have to choose one of them, so I walk up here to this place where the objective value is z. Okay, my claim is that regardless of what else this polytope could be doing, the simplex method will never, well, first off, if there are any other vertices down here that have a lower objective value, once the simplex method gets to an objective value of z, it will never go to any dictionary with a lower objective value. We know that for sure. It turns out that it will also never visit a distinct vertex of the polytope with the same objective value. So if it ever gets to this vertex, it will never visit this one, under any circumstances. The only time that the objective value stays the same between iterations is during a degenerate pivot. And a degenerate pivot involves standing still at one vertex. It doesn't involve going to a different vertex with the same objective value. And so it's reasonable to assume that although there are a certain number of dictionaries that could exist, structurally, the simplex method really won't, it's pretty unlikely that it will visit a large number of them, because there are some that are completely infeasible, so some that might be sort of, I don't know, down here or something, or some that might be up here that are infeasible because they don't meet all the constraints, and in the path that the simplex method takes, as it progresses through the algorithm, as it goes through the different vertices of the polytope, at each step, a large number of dictionaries are ruled out because their objective value is too small. So this assumption that the total number of dictionaries could be somewhere around here doesn't necessarily mean the algorithm's performance is going to be this bad, because it's a bound that we're drawing and maybe it's too loose of a bound. On the other hand, what I can do to try and see whether or not it gets exponential is to decide whether I could construct an LP where if I run the simplex method, it literally goes to an exponential number of dictionaries. Maybe not an exponential number that's this large, but if I can find an LP where the simplex method does take an exponential number of steps, that would be a pretty good evidence that it's an exponential algorithm. And unfortunately, I can. So the claim here, for any n, there is a linear program on n variables, so an n-dimensional linear program with 2n constraints that requires at least, so big omega, of 2 to the n pivot steps. So not 2 to the 2n, I guess, that's helpful, but 2 to the n pivot steps using Bland's rule. So it's too bad. If this claim turns out to be true, which it is, it's too bad. I mean, that means the simplex method is exponential with Bland's rule. But you could look at that and think, well, hey, Bland's rule we know isn't performance-oriented. Bland's rule, really, the reason we use it is because we want to avoid cycling. We know that because Bland's rule doesn't care like what vertex comes next, as long as we leave the current vertex, it chooses the entering variable to be the variable with the smallest index, not necessarily the variable that gets us closest to the optimal solution, then maybe it's no surprise that Bland's rule might meander around the polytope a bit more than it has to. So just because Bland's rule results in exponential performance doesn't mean that all is lost. So here is an LP and its feasible polytope. Now notice that this feasible polytope isn't feasible at 0, 0. And typically running the simplex method, as we know, or solving an LP with the simplex method might actually involve running the simplex algorithm twice. Once to solve the auxiliary problem, once to solve the original LP. The way I'm going to address this is I'm going to say, let's just analyze what happens if I solve once I find a feasible point of my LP to solve the original LP. If that takes exponential time, it's reasonable to conclude that the auxiliary problem could as well. So we'll just talk about that. Before I do, I want to take a look at this problem a bit. So I've constructed this LP, and we'll notice that I'll show a few other examples. It has a very regimented form. Notice that my objective function is maximize y. So it's actually pretty easy for us to look at the diagram and tell that this is the optimal solution. This maximizes y. So that's an easy one to look at. We're going to show that with Bland's rule, for some reason, every single vertex of this polytope gets visited. So there are 2 optimization variables, it's 2D, and there are 4, so 2 to the 2, equals 4 vertices of my feasible polytope. And I'm going to visit all of them with Bland's rule. And we're going to look at this and say, well, that's bad luck. So here is the dictionary I get to when I solve the auxiliary problem to find an initial feasible solution. And I'm down here. And I said earlier that this is the optimal solution. So we're at our initial feasible point is 1 step away from the optimal solution. But that's not how Bland's rule works. Bland's rule has 2 choices of entering variable, and it chooses W1 because W1 has the lowest index. If it chose W3, we would walk up this edge and we would end up at the optimal solution. But we don't. We choose W1 and we pivot over here. And on these 2D polytopes, it becomes really easy to know what's going to happen. As soon as you've taken one edge, because you know that the algorithm never goes backwards, you sort of now know that the rest of the path is going to do this. It's going to walk all the way around. And it does. All right, and then, Captain Obvious here, the slide is telling us this is a deformed square. So yes, it's a deformed quadrilateral. On a 2D LP with this number of constraints, that's sort of what you're going to get, unless one of the constraints is superseded, is irrelevant. But fair enough. The reason it's bringing that up is not just to be obvious, it's to actually observe that this LP that I constructed to demonstrate this point was created with a construction that lets me make the feasible region as close as I want to a real square. So like the unit square would be from 0 up to 1. It would be the boundary of this diagram. This LP, for the sake of being easy to read, the feasible region is sort of stuck in the middle. But if I were to adjust the construction a bit, I could make an LP in the same family. So here, you might want to look, if we compare the structure of these, notice how it's 4x and then 1, 4x and then 3, and then 4 and then 0 and 4. Notice that here I've got 100x and 1, 199, and then 100 and 0 and 0, and 100 and 100. So you can see there are some similarities in the construction. By adjusting these coefficients, I can actually make the feasible region sort of asymptotically approach the unit square, but just a little bit deformed. So it's twisted just a bit. You can see that here the initial feasible solution isn't quite 0, 0. Here, the vertex is a little bit off the x-axis. And similarly, up here, the optimal solution is just a little bit off of 0, 1. But I can, by using larger and larger numbers here, I can actually make this thing look as close as I want to an actual square. And the same problem occurs. If I run through the system, it's going to be much more ugly arithmetic, but I will end up walking around the outside of the polytope and ending up with this sort of horrifying set of fractions that I have to work with. I can construct the same type of example in 3 dimensions, and I'll show the general construction later, but it's worth observing that the first couple of lines look pretty much just like the previous example. I just added more constraints to accommodate the new dimension that I've added to get into 3 dimensions. The objective function is now maximize z. And this is my z-axis on the diagram, so this is going to be my optimal solution. It may not be obvious that this is actually at a higher altitude than this point here. And it turns out that if I use Bland's rule, I will start, this will be my initial feasible point, and I will walk all the way around. I will basically go on a Hamilton tour of the vertices of this polytope. I will visit every single one of them. And so I've got 3 optimization variables, So I'm in 3D, and I will end up visiting 2 to the 3 equals 8 vertices of this polytope. And that's bad news. And I can construct analogous examples for any number of dimensions, 4 dimensions, 5 dimensions, whatever, although it's harder to draw diagrams of those. So in this case, the polytope is a deformed cube. Notice that it does, you can see, especially if you look at this face here, you can sort of see an echo of that feasible region from the previous example. And it turns out it's a deformed cube. We know already that if we create actual cubes, the feasible region will have 2 to the n vertices. So let's see what happens if I try running the simplex method. So okay, I initialize, I end up at this point here, and again, the optimal solution is right upstairs. I mean, it is right above where I start. And we look at this and say, well, this is just Bland's rule being stupid. Because Bland's rule isn't performance oriented, for some reason it can't see this, and so it tries and takes the long way. And we actually will notice it does pivot through every single vertex of the polytope. Everywhere it has the optimal solution in sight, it goes in the wrong direction. And so it visits every single vertex of this polytope, and the polytope has an exponential number of vertices. And so that's unlucky. And actually, yeah, I've got another example here. I can make the feasible region look very, very close to an actual cube and get exactly the same behavior. The cube is deformed just enough that it messes up Bland's rule. And in fact, the arithmetic is so ugly here that the typesetting actually cut off a column of this dictionary. This is supposed to be W1, not a constant column. So that's unlucky, but we still don't have too much of a reason to be pessimistic. We can say, oh, well, Bland's rule is not performance-oriented. This is too bad. This is one reason why Bland's rule isn't great, right? Why we want to use a pivot selection rule that takes the objective value into account. And it's worth considering that, yes, Bland's rule is our only hope if we want to avoid cycling, but we don't only have to use Bland's rule. If you were implementing a simplex solver, of course, and you will, of course you don't want the algorithm to cycle, but if you think about when cycling can possibly occur, you might realize that at most vertices, assuming you're not stuck in degeneracies all the time, as long as you're not at a degenerate dictionary, you don't need Bland's rule because cycling can't occur. Cycling only occurs when you're at a degenerate dictionary. And so what you could do when you're implementing the algorithm is, if your dictionary is non-degenerate, use the largest coefficient rule. If your dictionary is degenerate, then maybe even then use the largest coefficient rule. But if you end up stuck at the same dictionary or the same vertex for, let's say, 3 steps or more, then switch to Bland's rule until you change vertices and then switch back. That would be enough to prevent cycling. So we think, okay, fair enough, this is just Bland's rule. Here is the general construction for how to give an exponential performance with Bland's rule for n dimensions. It says the simplex algorithm is big omega of 2 to the n, which is true. It's going to take 2 to the n pivot steps, and therefore will take at least 2 to the n time. Although, keep in mind, the actual complexity, if it took exactly 2 to the n pivot steps, would be 2 to the n times the running time of an individual pivot, which would be times m times n. My claim is that really, once we know that it's going to be exponential, this m times n does contribute, certainly. We can't throw away multipliers like this with asymptotic analysis, but certainly it's a lot less of a concern to us. We really want to do something to this number as opposed to this one. So fair enough, Bland's rule's lousy, but Bland's rule's job isn't to get us to the optimal solution quickly, it's to keep us from going around in circles forever. And it's worth considering, of course, that if I feed this example in, using a different pivot selection rule, so here I am at my initial feasible solution, and the optimal objective value is right here, it turns out that if I try and solve this with the largest coefficient rule, well, let's see, what do I choose? Largest coefficient here, I guess, is W5, and so I pivot W5 out, and there I am at the optimal solution in one step. So the largest coefficient rule makes short work of this counterexample for Bland's rule, as we might expect it to, because Bland's rule's job isn't to be able to find the solution quickly, just to escape from cycles. So we want to blame Bland's rule. We want to continue being optimistic. Unfortunately, this insight of creating this deformed cube that sort of fools our pivot rule to walking all the way around, this insight can be applied to other pivot rules, including the largest coefficient rule. So we can see there is in fact an LP that I can construct in n dimensions that will result in the largest coefficient rule taking 2 to the n pivot steps. Here is the example for 3 dimensions. So first observation, clearly the construction is different. You might also observe this construction is initially feasible. There's no auxiliary problem that I need to solve. The insight behind this is a little bit less obvious because the feasible region doesn't really look like anything. It's this strange spindly shape. It's a deformed cube again. It actually does have 6 faces and 8 vertices, but it's been deformed so much that it's hard to see what's going on. So what's actually happening is it's been deformed by really, really stretching it with each successive dimension. So the x dimension, I think, goes between 0 and 1. So this is the x dimension here. The y dimension goes between, I think, 0 and 9. And the z dimension goes all the way up to 81. And because notice how this tip up here, which is actually at x equals 0, the tip of this little spike, this is the maximum, this is the optimal solution. And it's not obvious looking at the objective function that that's going to be the case. The optimal solution actually occurs when x and y both equal 0. But notice how we've cleverly devised this objective function that might fool the largest coefficient rule, because the largest coefficients are on x and y, even though z is going to be the thing that brings it home for us, that actually gives us our optimal solution. So before we can talk about that, we've got to find some way of visualizing this. So what I'm going to do is, this is a stock visualization of this feasible region. For the sake of understanding what it really looks like, I'm going to stretch the axes of the diagram. So what I've done here is the z-axis still goes from 0 up to 81. And the shape that I'm showing here is the same shape as the previous slide. I've just stretched the diagram. The x-axis goes from 0 to 1, so I'm using non-uniform scaling, and the y-axis goes from 0 to 9 on this diagram. So when we do that, we get this shape, which does look a lot more familiar. It does look very similar to the shape we had back in the example of Bland's rule. Not identical, though. Okay, so now we see this, and let's try running a pivot. So here's our initial dictionary. The optimal solution, again, is actually right above the starting point. If I were to walk up here, I would get to the optimal solution. And in fact, this is a case where the largest increase rule would probably get me there in one step. But unfortunately, the largest coefficient rule stares at this and says, oh, 9x, that's the largest coefficient, so let's increase x. And if I'm standing at this point, where can I go to increase x? Well, I have to go along this edge here. So I end up here, and we can see this is already sort of bad news. This is a sign that there is a way of fooling the largest coefficient rule, even if it's standing right next to the optimal solution. So it might not surprise us that we could find an LP that fools it at every other step as well. So we walk one step, sure enough, there we are. Now the largest coefficient is y, so we walk over here, we increase y, we end up at this vertex, and now the largest coefficient, let me see, the largest coefficient is actually W1 here. Although we could walk upstairs and end up on the second floor, we don't, because the largest coefficient is W1, which corresponds to a constraint, and it actually takes us back here. So we're still down on the lower floor. We have now visited every single vertex at z equals 0. Z has been outside of the basis as long as it possibly could. Now we finally walk upstairs. And again, we are one edge away from the optimal solution, but just by bad luck, the entering variable is x. So how do we, currently x is 0. It's non-basic, so we know it's 0. Where can I go to increase x? Well, I can walk this way. And so again, we make the wrong decision. We walk as far away from the optimal solution as is possible given the circumstances. And if we keep going, we indeed end up visiting every single vertex before getting to the optimal solution. And so it turns out that this holds on any number of dimensions, that if I apply this construction here to any number of dimensions, then I can produce this LP that requires 2 to the n pivots, or 2 to the n minus 1, so big omega of 2 to the n pivots, with the largest coefficient rule. So although earlier it was tempting to blame Bland's rule, I can come up with a similar insight that allows me to break the largest coefficient rule as well. And here's the full construction for any number of dimensions. It turns out these constructions are related. They are examples of families of constructions that are called Klee-Minty Cubes because they were invented or first published in this paper from 1972 by Klee and Minty. And it turns out that Klee-Minty cubes can be derived for pretty much all the pivot rules that we've seen that are performance-oriented. And so there doesn't seem to be much evidence that the pivot rules that we have on hand, any that we're aware of, actually give us polynomial performance. There are some that are better than others, maybe in the expected case, maybe in the worst case, but the worst case seems to always be exponential. which is too bad. It's also true that the construction is different for each pivot rule. We saw earlier that the thing that breaks Bland's rule doesn't break the largest coefficient rule. So when we have these constructions that are based on deforming a cube, they're called Klee-Minty cubes. Unfortunately, a lot of sources, when they talk about Klee-Minty cubes, cite this paper. And there is this thing that people do in academic writing, and I'm not judging anybody here, but there's this thing people do where when they use an important fundamental result, they will just cite the paper that the result is always attributed to without even reading the paper. I have a feeling, because of how hard it was for me to get a copy of Klee-Minty's original paper, I had to get somebody to scan a paper book at the library and send me a PDF. Because of how hard it was for me to get that, I strongly suspect that many of the people citing Klee-Minty they've never actually seen Klee-Minty's paper. Because when I finally got Klee-Minty's paper, after reading tons and tons of other sources, books, including our textbooks, that cite this construction and other related ones to Klee-Minty, I was pretty surprised to see that this construction doesn't appear in their paper at all, and neither does this one back here. Constructions like this that frame it in terms of a maximization problem or an LP in any way are not found in Klee-Minty's paper. There is something close to the Bland's rule construction in Klee-Minty's paper, but stated in a much more formal way. The construction here for the largest coefficient rule doesn't seem to appear directly in their paper, although it's reasonably clear that their paper does prove the largest coefficient rule could require an exponential number of steps. Actually, having an explicit construction is not something that their paper does. Every author that talks about it, though, just cites that one paper, even though the derivation seems to have come from somewhere else, which is pretty annoying. So please, if you're doing research out there, your research could be very important in many years. Please make sure that if you use some construction, you actually cite where you get it from. So somebody teaching a course on your subject 40 years from now can figure out who actually authored these things. And so it's worth considering that Klee-Minty cubes were invented by this paper, but there are lots of different formulations, even for a particular pivot rule. So this isn't the only construction that results in exponential performance for the largest coefficient rule. There are lots of others. If you're interested in them, we can talk about them. Come to the office hours. There actually are a lot that are sort of clever, that don't require as much setup, but still produce the same result. None of them appear in Klee-Minty's paper. So for full disclosure, the one that I used came from here. It came from something called the Encyclopedia of Optimization. As far as I can remember, they cite it to Klee-Minty's paper, which, as I've said, I'm not really buying. I'm not sure why we do this. But in any case, these are all examples of this broad family called Klee-Minty cubes. So it turns out that although we've only seen the examples for Bland's rule and largest coefficient, we can construct Klee-Minty cubes or something similar to that for all of the other rules that we're likely to use. And that means that we could assume functionally that the simplex algorithm, as far as we know, until we invent a better pivot selection rule, does indeed have exponential worst-case performance. So that's too bad. It isn't even known whether if we create the ideal pivot rule, so if magic exists and we can actually evaluate the magic pivot rule that I talked about before, we don't even know whether under the best circumstances a polynomial number of pivots is feasible. So it could be that even if we had this magic pivot rule that would always choose the best possible pivot to get us to the optimal solution as quickly as possible, we still don't know whether that would be exponential. And just to sort of elaborate on this a bit, suppose we have a polytope. Let's just use this 3D polytope here as a point of reference. So what I could do is I could represent, if you notice, because I'm walking along edges of this polytope between vertices, really what I'm doing is walking along edges of a graph. I could take each vertex of my graph, or each vertex of my polytope, and I could make it a vertex of this graph. Whoops, actually, hold on a second. Maybe we'll do it like this. Okay, sorry, I'm going to make this graph. I'm going to try and draw. So we'll make vertices for this bottom face here. So that's this. That's this. That's this. Nope. That's this, and that's this. Okay, so there's 4 vertices for the bottom layer, and then similarly I'll make 4 vertices for the upper layer, and we just connect them by edges whenever the polytope. We can turn any polytope into a graph this way. Okay, so this vertex is connected to this. It's connected to this. And it's connected to this. this vertex here is connected to this, and this is connected, whoops, I started erasing. This is like this, and then we've got this. So we end up basically constructing a planar, or whether it's planar or not is irrelevant, representation of this cube. The reason why I care about that is because if we now consider the process of performing pivots, I'm standing at this vertex here, which pivot do I choose? If I know that my optimal solution is at some other vertex, so suppose it were at this vertex here, the best pivot sequence would be the shortest path between my starting point and my ending point. So if I'm able to traverse my entire polytope in advance, I could work out the length of a shortest path. I suppose maybe this is a shortest path. And that's when I talk about the magic pivot rule, that's really what I'm talking about. So if I scroll back over here where I was making this point, suppose we construct the graph for whatever polytope we find ourselves working with. All right, and I don't mean this graph I'm drawing, I'm just making up one from scratch here. We have no idea whether this graph is actually going to correspond to a real polytope. Okay, so I've got this graph here. This is my polytope. Here is my starting vertex. It happens my optimal solution is here. When I'm standing at this vertex, suppose that the objective value of the neighboring vertices behaves strangely. So it's 10 here, it's 11 here, and it's 1 at this vertex. So that means the largest coefficient or largest increase rule may well choose one of these two vertices as the first one to visit after my initial one. But we know the shortest path between the initial vertex and the optimal solution is this one. The magic pivot rule is a notional, idealized pivot rule that at each step, whatever vertex you're standing at, it somehow magically knows where to go to get you as close as possible to the optimal solution. So obviously we don't have any way of implementing that for a lot of reasons. We could do brute force search, which is to say get all the vertices of the polytope, generate the graph, run a shortest path algorithm, and then work backwards from that. But that would take exponential time, so that wouldn't be worth it. What this is actually trying to get at, it's not even known whether even if the magic pivot rule were something we could evaluate, we don't actually know whether given an arbitrary polytope and two vertices, so I pick a starting vertex and an optimal vertex, we don't even know whether the shortest path between them is of polynomial length. So what I'm saying is, if I take an arbitrary polytope, any vertex could be the optimal solution. So what I care about for the magic pivot rule is, what is the longest length of the shortest path between a pair of vertices on this graph? And it turns out that that quantity has a name in graph theory, which is the diameter of a graph. We'll use the term graph theoretic diameter because the word diameter also has geometric implications. So it turns out that the minimum number of pivots to solve an LP over a particular polytope will be equal to the graph theoretic diameter of that polytope, which is the longest length of a shortest path between two vertices. And so people have done research about diameter of graphs, certainly, but also the graph theoretic diameter of polytopes. And we know how to, if you hand me an LP in standard form, we actually know how to decide what that polytope looks like, at least in an abstract sense. So if I have an LP with n variables and m constraints, and I mean m constraints, m explicit constraints, not including the non-negativity constraints, then each of the m constraints could contribute up to one facet or face to the polytope, and each of the non-negativity constraints could also do that. We know, though, however, here's a polytope in 2 dimensions. Here's a polytope that sort of looks like a square. This LP had to have at least 4 constraints, including the non-negativity ones. But it could have had more than 4. There could have been some constraint out here that got superseded by the other constraints. So that's why I say up to this number of facets. If I have n variables and m constraints, the number of facets on the polytope will be at most this number. And there are results about that. So if I look at a polytope in d dimensions with a particular number q facets, there are these theorems that people have proven. I think there's actually been a better result since this one, which is the graph theoretic diameter is at most, the most recent result by Todd would be this number. If we now plug in what we know from linear programs into that, so the number of facets is q, which is in an LP would be n plus m, and then d would be the number of dimensions, which would be the number of optimization variables, or n. And then this would be log base 2 of n. And if we notice that's just n plus m minus n, that gives us this number. So what this is saying is, if you hand me the polytope for any LP in n variables and m constraints, it could, the graph theoretic diameter, which is to say the minimum number of steps you might have to take between any two vertices, could be as much as this, as far as we're able to prove. It could be lower. We just can't prove that it's always, that under no circumstances is this upper bound, could we improve on this upper bound? And so that means that there could be some LP with m constraints and n variables that does require this number of pivots, as far as if Todd's bound is the best bound we can come up with. And of course, this is not polynomial. It's, depending on what definitions you use, you might call this quasi-polynomial. It's certainly sub-exponential, but there's some disagreement about what those terms actually mean depending on which source you use. So it's not quite exponential, but it is not polynomial. Now, this is all sort of irrelevant because as far as implementing solvers go, there is no way to evaluate the magic rule. Like, we have no way of actually getting the shortest path between two vertices, especially because I don't know how to ask, for the shortest path between the start vertex and optimal vertex until I know where the optimal vertex is. So this is something that's very interesting theoretically, that's really important to study, but it doesn't have any direct implications on our ability to write a solver today. There was this interesting conjecture, which was disproven about 10 years ago, which was the graph theoretic diameter of a polytope in d dimensions with q facets. This is a conjecture about graph theory that stemmed from analysis of linear programs. The conjecture was that the diameter was at most this. So the ideal pivot sequence for any LP would take at most this number of pivots, which is pretty good. Actually, you know what? I'm thinking that maybe I've gotten these variables in the wrong order. So look at the posted slides for this. I'm realizing that the number of dimensions is probably less than the number of facets. So for a correct statement of the Hirsch conjecture, take a look at the posted slides. And it was a famous conjecture for many years. It stemmed from this original analysis of the simplex method, I think 50 years ago. But it was eventually disproven in 2011 with a counterexample. So there was some wishful thinking there. The fact that it was shown to be true in many subcases is sort of a hint that the worst case running time of the simplex method doesn't say that much about its performance in practice. The average LP doesn't tend to require an exponential number of pivot steps. This is, despite the fact this is disproven, if you're a grad student and you want to look into this, this would be a great presentation topic to talk about where this conjecture came from, but also what were these subcases and sort of what was the insight behind that counterexample from 2011. So the simplex method is exponential. We just have to get used to that. But it turns out that solving linear programs, that problem itself is solvable in polynomial time. There are ways to solve linear programs that are polynomial. And that, obviously, the question, that might be coming to your head is, okay, Bill, wait a minute. So you've just spent 6 weeks teaching us about an exponential time algorithm when there were these polynomial time algorithms all along. What gives? I'll address that in a minute. First, I'll talk about these other algorithms. So as far as proving that LPs can be solved in polynomial time, there was something called the ellipsoid method, which was formulated in the early 70s and proven at the end of the 70s to be polynomial, to solve LPs. It was an example of one of those algorithms that, although it is nominally a polynomial algorithm, the constants involved were so big and the algorithm itself was so difficult to manage that it wasn't actually competitive in practice. An implementation of it would not be faster than the simplex method on any LPs that needed to be solved. There was, however, in the mid-80s, this algorithm called Karmarkar's algorithm, which is still used today, an example of an interior point method which can solve linear programs in polynomial time. And it was competitive with the simplex algorithm because not only was it polynomial on paper, but it could actually be implemented in a way that could solve linear programs quickly. It was also the subject of a very famous software patent case because Karmarkar designed this algorithm and published it in a journal somewhere, but at the time was employed by a private corporation, which, as I'm sure you know, when you work for a private private corporation, especially in a role like, even as a researcher, but in a development role as well, often you have an agreement with them where they own everything you create. And this corporation therefore ended up with a patent to this algorithm, which resulted in a very famous, it was a famous example of some of the difficulties of software patents, which I would love to get into, but I won't. If you've taken a course like Seng 401, you might have even discussed this algorithm. If you want to talk about software patents, come talk to me in the office hours. But basically the concern was Karmarkar's algorithm was patented, which meant anybody that wanted to use it for anything had to pay royalties to the owner of the patent. But there was an argument that Karmarkar's algorithm was just a statement of mathematical facts. And maybe also there was an argument that really the algorithm that Karmarkar was proposing was a variant of a more general approach. So why was it fair that we could patent that and then force anybody using it to pay royalties? Now the patent is expired now, so we no longer have to worry about that, but it was an early example of one of the dangers of allowing software to be patented. So then there's the question, why did we learn the simplex algorithm? Okay, the first reason is that even these days, if I use a good quality simplex implementation, it is pretty fast. And it's likely to outperform interior point solvers like implementations of this and other algorithms that don't use the simplex method in a lot of cases. They've done empirical studies that verify that on average they're about equal. I think more. The data I've looked up has said if you try running a large number of LPs through both simplex, good quality simplex implementations and interior point solvers, neither really has a huge advantage. Some are better on some problems, some are better on other problems. I have tried this, and you can try this too. If you get the SciPy toolkit, inside SciPy there's this module scipy.optimize, which I think, and the relevant function you want is .linprog, which solves linear programs. And one of the parameters to it is what method do you want to use? Do you want the simplex method, the revised simplex method, or I think it offers a few interior point methods. And I've tried this out. It turns out that on some LPs, the simplex method works better. On some, the interior point method works better. On some, one method or the other just fails completely. It just gives the wrong answer for a lot of different reasons, because there can be numerical issues that get in the way of whatever the solvers are doing internally. So that is one reason why the simplex algorithm actually is still very important. It's still widely used. It's considered to be very efficient. It doesn't usually require a very large number of pivots. And you've noticed this. You've worked with LPs that have a reasonable number of variables and constraints, and often you get the solution in one or two pivots. So it isn't the end of the world that there are some isolated inputs that have this exponential performance. And it turns out that, yes, like a lot of other algorithms, the worst case inputs of the simplex algorithm seem to be pathological cases. They don't seem to occur very often. There's also this. The fact that the simplex algorithm, because of the properties of the LP that it exploits, is useful as a theoretical device. So we can actually use the algorithm in proofs to make statements about linear programs in general, not just about how to solve them with the simplex algorithm. And I could argue that we've already done that because proving Bland's rule worked required using the algorithm, but that doesn't really count. That's not fair because that was a proof about the algorithm. In the next lecture, the next set of slides in my slide sequence, I think that'll be next week's topic, not the next one. I think we're going to take a little break. But the next topic, which is a very important topic, we're going to use in the next of the sort of ugly proofs we have to cover, we are going to use the simplex algorithm as a proof device, something that I don't think would be as easy or feasible with one of these other algorithms. That's one other reason why we really have to understand the simplex algorithm, because it exposes a lot about what linear programs truly are. And so in the next lecture, we'll see that it can be used inside of proofs. And also, of course, when you want to go implement a solver, if you knew what those other algorithms were really doing deep down, you'd probably agree that implementing the simplex algorithm is a bit easier than implementing those other algorithms.